figure out how to, like, we could ask someone else how to do that.
Well, there's a lot of Blackboard functionality which isn't tools I've used.
Yeah.
And some of the things you referred to, you've probably experienced, you said, on online classes.
I've had it in-person classes.
In-person classes too.
Yeah, for sure.
Like, we have, like, I have a psych class, pretty much, it's like, it has a, great questions discussion board, which pretty much is like, if you, like, had a question and you didn't want to email the whole class about it, you just would post it there, and she would give extra credit if you were the first one to answer the question. That was just her method. Like, if you first gave a good answer, then you get extra credit. Like, you could set it up.
I can't even imagine having to monitor that so that I could
asking for
give
the
up.
credit.
I'm just
that's
like,
what she does. That is what she does.
Noted. I'll look into it, but I do need to figure it out, and it might be something where, well, it's an administrative side of the Blackboard, so I gotta find it.
Yeah.
Okay, so we got one more lecture of new content preceding next week's exam. Yes.
Sorry, I have one last question about mastering chemistry. There's been a couple times where mastering chemistry is giving us the wrong answer.
Yeah, there has.
Can you
So
post that somewhere so we don't study incorrectly?
So when I am not going to go through every single homework and verify every single answer on the homework, but I have a meeting at 2 o'clock with the Pearson representative and the regional director for Pearson, and they're going to hear all about Blackboard. So in the meantime, what I really want everyone to do, if you find a wrong answer or you post the correct answer and it's not accepted and then they say this is the correct answer and it's the same answer, I need you guys to send that screenshot of that event to their help people and CC me, so I have a catalog of all the things that are, I'm on video, incorrect with Blackboard. This has never been an issue historically with Blackboard. With mastering. I've been using mastering for a while. And mastering's historically been the most robust, best edited, most correct homework platform. And something has changed. So the best thing we can do is screenshot report, CC me so I can catalog. Because I'm aware of a bunch of them. One came in, I became aware of another one last night. So, okay. Just every homework platform has issues periodically. This has gotten to a point where, and this one's not even on hard stuff. This is getting things that are wrong that have never been wrong before. So I don't know why, like in the first chapter where it was with, like you said, hey, what's the conjugate acid to ethanol? Yeah. And they're like, oh, it's OH3. Yeah. Like, where did that come out of?
What?
I got ticket the first week and never.
And when you don't hear back from a ticket like that, that's good to know, because I'm going to mention that in the meeting. Has anyone gotten a response by sending a ticket in?
No.
Not one. Good to know. And this is really opportune because we were considering moving the Gen Chem platform back to mastering. And we would have, except that this has not been rolling out like it should. So, good news is everybody's on the same boat, and that's an easy adjustment to make on homeworks. So that's a great, yeah.
Will there be an updated syllabus posted so we know exactly?
Yeah. Yep, I need to update syllabi and submit them to the college anyway. So the exam will be on Wednesday. So, it'll be on Wednesday.
You have a whole class period to do it?
Yep.
Nice.
Yep. Normal class period.
Is it online? You said like a computerized exam.
Okay, so yeah, I totally have the wrong. Okay, nope. Face-to-face exam here.
Okay.
Face-to-face exam in class.
What's Scantron sheets?
Hmm?
Scantron sheets?
Yes. Scantron sheet.
Oh.
Multiple choice. Yeah.
Right.
One of those blue ones.
Yeah.
I totally
Wait,
told
the
you.
why blue ones?
Nope.
For what?
Nope. The,
They're like 25 cents.
Yeah.
Oh, that's the
Yeah. So.
Scantron sheets are?
Oh, I specifically got like 25 cents. I know people are gonna forget.
Yeah. So the So yeah, in class. Okay. Let me make a quick note here. It will be. This one will be all multiple choice. There will be no mechanisms on this exam. Okay, let me get my caveat. There may be one or two non-multiple choice questions, but it will be overwhelmingly multiple choice. Okay, so let me see here. Yes.
Are you allowing the periodic table or calculator?
You will not need a calculator for this exam. And I'll include a periodic table. Even though, by now, carbon, nitrogen, oxygen, and halogens and hydrogen, everyone's got those. If anyone actually references the periodic table on this exam, there will be very little need to reference periodic table, but I'll include one.
There's quite a few equations in chapter 2. I'm just wondering. So
There are. There are a few equations in chapter 2.
We don't have to do logs that aren't, unreasonable, right? Like all things base 10, you'll only give us base 10s then?
Well, if you can't do the log base 10 of 3.3 in your head right now, then you need to get, no, I'm just kidding. You're not going to need, you will not need a calculator for this exam. I'm not saying you're not allowed a calculator. I'm saying you're not going to need a calculator.
So we're allowed like a non-programmable calculator.
You can bring a non-programmable calculator if you want to.
Can we bring our model kits?
Yeah.
Okay.
Yeah, you can bring model kits. Yeah, non-programmable calculator is fine.
Are we supposed to memorize all the equations?
Yes. That's my default answer. Know all the equations. Know all of the things.
All the things.
Know all things. Knowing relationships between things is a good thing. Whether or not it's on the exam, you should know it. Most common question, will this be on the exam? Yes, that's my default answer to that question always. Y'all ready for multiple stereogenic centers?
Let's do this.
Yeah. Okay, cool. That's as excited as I'm getting this
Did
morning.
you record already?
Yes, I am.
Okay.
So they got all that, which is super confusing because they're like, we're in the online class. This is not pertinent to us. Well, some of it might be. Multiple asymmetric centers. So it's really common for compounds to have more than one central carbon, which has 4 different groups attached to it. Let's say 3-chlorobutanol. So this is 3-chloro, 2-butanol. Because we number from the side nearest the alcohol because it's a functional group. And here we have a carbon which has 1, 2, 3, 4 different groups attached to it. And here we have a carbon with 1, 2, 3, 4 different groups attached to it. So both the 2-carbon and 3-carbon are chiral carbons. So what do we do with this? What are the different combinations of things that can happen? Well, like we mentioned last class, if the number of chiral carbons is n, so in this case n equals 2, then there's 2 to the n possible different conformations for this compound. So there's, in this case, 4 possible combinations when we have all the different chiral centers and all their possibilities. So let's walk through these. And you're going to see, I'm going to lean on the spatial model versus the Fisher model for all these discussions. Oh, it's a head scratch, not up. Okay. So let's see here. Let's start with this one. So for this particular variation, we can draw the mirror image. And let's see here. So hydrogen near side, that is over here. Hydroxyl near side, methyl near side, methyl away. So this is mirror image. This will be non-superimposable. We've inverted this stereocenter and we've inverted this stereocenter. So this is going to be a pair of enantiomers. But if we do this again, and I have about this much space, so I need to make it a little. So what I've done here is I've just taken these two and flipped them and redrawn it. So I'm flipping the stereocenter, but I'm leaving, let's see, let's flip it up. Yeah, leaving this one the same. So we've inverted one stereocenter and left this unchanged. We can take the mirror image of this as well. And because this is a non-superimposable mirror image, this will be a pair of enantiomers. Enantiomers. So this is our 4 different possibilities of how 3-chloro-2-butanol can be spatially arranged. And we have 2 possible pairs of enantiomers in here. Now, here's the thing. Are these 2, we'll just call this versions 1, 2, 3, 4. Are conformers 3 and 4 superimposable with conformer 1? But are they mirror images?
Yeah.
All right. So now we have a new type of stereoisomer. Enantiomers are non-superimposable mirror images. What we have now is a new term, diastereomer. And what this is it's a non-superimposable non-mirror image. So it's not a mirror image, but it's still not superimposable. And by superimposable, remember that what that means is it's not the same thing. Superimposable is the same thing. Right? So it means it's a unique structure spatially, but it's not a mirror image. And we have a bunch of combinations of that. So 1 and 3 are diastereomers. 1 and 4 are diastereomers. 2 and 3 are diastereomers, and 2 and 4 are diastereomers. So we have more diastereomer relationships in this pool than we do enantiomer relationships. Important differences between enantiomers and diastereomers. Enantiomers are chemically, physical property-wise identical. They're very hard to separate. They're very hard to treat differently via different chemistries. Diastereomers are chemically distinct. So even though they are all the same things attached to the same things, because they are not a mirror image, they are more different than enantiomers are. So that's why we have this new term for them, because they're chemically and physical property-wise distinct, whereas enantiomers are not.
Can you say which ones are together again?
Okay, if it's a mirror image, it's an enantiomer. If it's a non-mirror image, it's a diastereomer.
So like 1 and 3 are diastereomers.
Right.
Okay, cool.
1, 3, 1, 4, 2, 3, and 2, 4. So if you are asked, is this a diastereomer or is this an enantiomer? What you need to do is take one of the compounds, do a mirror image, and then identify if the second compound is in fact that mirror image or not. So you just make a mirror image, and then you can do any rotation you need to align the functionalities between your mirror image and the second compound in question, and you'll be able to quickly identify, is this the same compound or is this not the same compound?
When you're doing that, manipulating C of the same compound, can you rotate around that CC
Yeah,
bond?
absolutely. They're all single bonds.
Okay.
So I can take this and rotate this. I can take this and rotate this.
Okay.
So if, for instance, over here, because I took a mirror image, the chlorine's over here. If I wanted to compare this one to this one, I would take this and flip it 180 degrees around. And then I would take this chlorine and, well, if I flip it 180 degrees around, the chlorine ends up in front, the hydrogen ends up in back, the methyl comes up, so this group's the same. And then the hydroxyl ends up in the back versus the front, so I know immediately that this is not an enantiomer to this, because it's not superimposable. But yeah, you can do whatever it takes. Another variation on this is cyclic compounds. So if we have a cyclic compound like this cyclohexane, and I'll put bromine and a methyl on it, how many asymmetric centers do we have here? 2. Right. Because, remember, we have an extra hydrogen here too. So each of these have hydrogens. So that's, they're there. We don't draw them in when we're doing these skeletal structures. But we have the hydrogen. And then if we say, well, this is one group, this is a group, if you go this direction, it's all carbon, 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 and then we have this group. If we go this direction, right out the gate, we have a unique carbon that's been modified with this methyl group. So because we don't have symmetry on either side of this, because this side is not the same as this side, this is considered a separate group from this one, and we have chirality. So that's going to be chiral. And for the exact same rationale, that will be chiral. So let's redraw this so that we could say, let's say somebody asked you to draw the enantiomer for this. Enantiomer is really simple. We just do the mirror plane. Near side corner, methyl. Down and still centered, bromine. So this is going to be an enantiomer. What if we wanted to draw the other two possibilities? Because we have two stereocenters, so 2 to the n means we have 4 possibilities. What would we do if somebody asked, draw the diastereomers for compound 1?
Flip over the.
Which one would you flip?
Doesn't matter.
Doesn't matter, right? So notice these are cis or trans? Cis. So could a trans variation, either trans variation, be superimposable with this? No. So if you see something and it's cis, the enantiomer is going to be cis. If you see something that is trans to this, like this is cis and you see a trans variation, you know that it's not superimposable under any circumstance, therefore it's going to be a diastereomer. So if we were asked to draw diastereomers for this, I could just arbitrarily put this bromine down instead of up, leave the methyl up. That's going to be one of our diastereomers. And then if I do the mirror image of this, and you're going to say, this doesn't look like a different compound than this because this one's down and this one's up and this one's down and this one's up.
But if you turn around, like if you were to turn it around.
Yeah, but to do it, I have to actually take this thing, because I can't just turn it.
Yeah, but I mean like.
Flip it like this.
Yeah,
So if I flip it like this, and just flip it over on, like that, you just flip it. You flip it like that, and re-envision it, this is down, when you flip it over, it'll be up. And when you flip it, this moves to the other side and goes down. And now you can see that this is switched and this is switched, and you can see why this is both a mirror image and superimposable. And not superimposable. So same thing here. If you were asked to identify your enantiomers, these would be your enantiomers. These would be enantiomers. If you're asked to identify diastereomers, for 1, 3 and 4 diastereomers to 1, 3 and 4 diastereomers to 2. Or you could say 3 has diastereomers that are 1 and 2, 4 has diastereomers that are 1 and 2. Either, just same thing. What about one, 4? How many chiral centers we got? Why do we have no chiral centers? Because magical? Oh, symmetrical. Magical. I like that. So just so you know, every now and then people get frustrated on tests and they enter things that are funny for levity. And I think it's like you have to laugh or cry, and they're choosing to laugh. And that's good, because every now and then somebody has something writes something really funny and I laugh. And like the angel on my shoulder is like, give him points anyway. And the devil's like, no. And I listen to the devil more than the angel when I grade. So, yeah, you're right. There's symmetry. So here we have one group in a bromine, one group with a proton, but we have this symmetry. So when we go this direction, we have CH2, CH2, CH3, CH2, CH2. Here, exactly the same thing. CH2, CH2, CH3, CH2, CH2. So, because this side is not distinct from this side, we don't have 4 distinct groups around this carbon, so it's achiral. Same thing here, for the exact same rationale. So, in this case, because you have a plane of symmetry, how do you distinguish between, say, version 1 and version 2? Cis and trans. Right. So this would be the perfect time to use cis and trans. You can also refer to these. Oh wait. Can you refer to these as cis and trans? Yes, but does it unambiguously name them? No. Right. So you are correct to say this is cis or trans, but it doesn't unambiguously name them. Whereas in this case, because they're achiral, cis and trans does unambiguously name what they are. And everyone thought that the nomenclature chapter was tricky. And still is, it's fair to be fair. But as we get more complex with our structures, you have to provide more detail to unambiguously identify what a structure is.
So how would you go about naming those 4 in a way that would distinguish them individually?
R and S.
Okay.
Can I do that here? Yeah, we can do that.
Yeah.
Actually, I have a couple other examples of RS coming up. So let's keep pushing through the required stuff, and then I think we'll have time to add back some of these examples for labeling things as R and S. Whenever you can't do something with cis-trans and you want to unambiguously name a chiral center, go to RS. Other news. We do have 2 OChem tutors identified. They're doing their mandatory trainings Thursday and Friday, which doesn't have them officially starting until it's too late to help with the first exam. But they will be available after the first exam. They might be available the day after the exam, but that's not really helpful.
Are you able to divulge their names so we can invite them to our study groups?
Like pizza?
They probably like pizza because they're also students. So they're going to be available for 2 1.5-hour blocks a week each. So there'll be a total of 6 hours of contact time available. I would ask you, because some of them are they're all teaching, or not teaching, they're all taking a handful of upper division classes and trying to graduate, that people don't ask them for more time outside of that, because they genuinely, we actually had a lot of good candidates say they just didn't have time. It's the trick of trying to get people who are trying to graduate to do something like this. So they're going to be present and have time and make time, but I'm going to ask the people, don't ask them for additional time on top of what they have agreed to be able to do already. Meso compounds, or meso, excuse me. Another variation. So, meso compounds have asymmetric centers, but they are not optically active. Which is really weird, because we just said chiral centers are optically active in the last class. And it turns out, generally that's true, but there's a circumstance in which it's not. And let's look at a circumstance where this occurs. So here we have a compound, a 2,3-dibromobutane. And is this carbon chiral? Yeah. What about this one? Yeah. So we have a pair of chiral carbons. So initially you would look at this and think, this should have optical activity. But if we draw the enantiomer of this, or what we go about the process of drawing what we would hope to be an enantiomer, because what's the definition of an enantiomer? Non-superimposable mirror image. This is what we get. So let's align. Let's see here. Let's see how best to align this. Let's leave this bromine here and out, and we're going to twist this bromine so that it's also out and down. So we're going to take this bromine and move it down to this methyl. So we'll have both bromines sticking towards us. Oh, because it's now away. So, whoop, it's not boron, that is bromine. So when I move this bond to top center, because this is away, it has to be out. Because this is out, it has to be away. So we've done a 180-degree flip. So if it's angled this way, you know it's going to be angled back when we do 180. Let's do the same thing here. We have a bromine sticking out here. And let's do the same thing and put the methyl up here. This hydrogen has to go to the back. This bromine now comes to the front. This is just this redrawn. This is just this redrawn. Those are the same compound. The mirror image is superimposable in this case. Because the mirror image is superimposable, this is the same thing as this. It's just drawn differently. So meso compound does have chiral centers, has asymmetric centers, but the mirror image is not a unique compound. So right now everyone's having a mild panic attack. You guys are being cool about it, but you're like, how on earth are we supposed to identify these? Do we have to do this for every single question? The answer is no. There's a shortcut. So let's see. If there is the book says a plane of symmetry, or a point of symmetry, then there will be a meso compound in the mix. It doesn't mean everything there's going to be meso, but it means that there will be a meso compound, meaning one of the pairs of one of the mirror images will be superimposable. So let's see what that looks like here. Here, it's really obvious. This bromine is mirrored, this proton is mirrored, this methyl is mirrored. Here, it's less obvious. But instead of having to do the full redraw, all we need to do is spin this to align the methyl, and if the other two groups are the same, then there's a mirror. So if it has the ability to have a mirror image, right? Because there's freedom of rotation, so this is spinning around in space, this is spinning around in space. The question is do they all align like a mirror? Another way you can look at this is, does it have the ability to have a mirror image or a plane of symmetry within the compound? Are the four groups attached to these two asymmetric centers the same? In this case, that's also an easy way to evaluate it. This carbon has a bromine, a hydrogen, a methyl, and one of these with a carbon, bromine, hydrogen, methyl. And this one has a bromine, hydrogen, methyl, and a carbon with a bromine, hydrogen, methyl attached to it. So both of these asymmetric centers have the same four groups attached to it. Therefore, of all of the different stereoisomers, there will be a meso compound. So how many total stereoisomers are there for compound 1? 3, right? Because we have two chiral centers. So 2 to the n equals 4, but of those 4, 2 happen to be superimposable, so actually it's 3. If we hold this the same and just flip these two, so we invert the stereo center, this will be now a what to this? It's a diastereomer, right? And the mirror image of this, which I'm not going to take the time to draw, will also be a diastereomer. Will the mirror image of this be meso, or will it be an enantiomer to this? It's going to be an enantiomer to that. Exactly. You guys are becoming pros. So I said plane of symmetry or point of symmetry. The book only says plane of symmetry. The reason I like the point of symmetry is because what we did now is all of the tools that we can use to evaluate it. We can lock one in place and spin it. We can look for, a plane here. But when you look for a plane, you have to spin something around after you put a plane in place. Well, a point of symmetry is a faster way. I love adding shortcuts to the book, right? It's like calculus. You spend your whole first couple chapters doing everything the long way. You're like, yeah, there's shortcuts. We all use shortcuts. So let me just clean this up a little bit. So point of symmetry means there's a point around which everything mirrors. And that point's going to be right there. This bromine mirrors this bromine. This hydrogen mirrors that hydrogen. This methyl in plane mirrors that methyl. Those carbons mirror the point also. If you connect the dots between the common atoms on either side of the plane, because this one's out and this one's in, so the line's going this way, this one's in plane, this one's out, this one's in, so the line's going this way, and they all intersect through a common space. Because we have a point of symmetry, you know that is a meso compound. The mirror image will be superimposed. So, if it's obvious, I mean, if it's drawn where you can see the plane, great. But you can also just say, okay, I've got 4 common sides. Is there a point of symmetry? If you have a point of symmetry, it's meso. Any questions before we do naming of multiple stereo asymmetric centers? I'll work my way through it. I don't know who was first. Okay, we'll go here and then we'll work our way over.
Okay, so I understand 2 to the n, we get 4, and I understand that, but I don't understand where the 3 comes from.
Because of the 4 possibilities,
Uh-huh,
2 of them are actually superimposable, meaning they're the same thing.
okay. So that cancels one.
If it's meso, it means this. If something's if something is superimposable, that doesn't mean, what that literally means is it's the exact same thing. If something it lines up atom for atom spatially, there's no difference in its identity. So it eliminates one of those 4. It becomes 3.
That's exactly what I was there.
Proof that if you have a question, somebody else has a question too. Yeah.
Just to check then, so if it had been, let's say n had been 3 instead of 2, would the answer have been would the answer have been 5 or 7? I'm just trying to check that.
If it was meso, if there was
one
meso.
was meso and there were 3
So 2 to the 3rd power is 8.
but would it be -1, or would it be you would have 2 sets that had pairs, so you'd have 4 plus 1. So that's.
It depends.
Oh, that's delightful.
Yeah. Depends on how many meso compounds you have.
1 was.
But you will have at least 1.
Okay. Got it.
With 3, I think it would be 1.
Yeah.
With 4, it could get more complex. With 4, it would be more complex. But I won't ask that on a test.
Okay. Cool.
And I've never seen that on a test. I've never seen a 4 asymmetric center meso question in a 300 level class exam. Now that I've said that, one's totally going to come on the ACS final and be like, ha ha.
So
And then you can throw fruit at the ACS people. Not at me. I'm not an ACS. Yeah, I guess I kind of am by affiliation, but any more questions? Okay, naming. The naming of all the things. Everyone's favorite. So, we had a good question. How do you unambiguously name things with multiple asymmetric centers? And what we're going to do is just name those asymmetric centers as R or S. So we're going to have a dial here? No, we're going to have a butanol. So this is a butanol, so we're going to number from the side of the carbon chain nearest the functional group. So this is going to be a 3-bromo 2-butanol. Or a 3-bromo butan 2-ol. That's also acceptable. So to distinguish between this and the other 3 possible stereoisomers, what we need to do is label the 2 carbon as R or S and the 3 carbon as R or S. So we have to prioritize. So on carbon 2, what's our highest priority group? Our hydroxyl group. What's our next? Or this one? Carbon 3?
Carbon 2.
Carbon, this is the center. So this is our center.
Oh wait, sorry.
So we have 1, 2, 3, 4 groups. The group around carbon 2. So this one.
Yeah.
All right. Carbon 3 would be our. Why?
Because it has it has the bromine following rather than the H's after.
Exactly, because our first bond away is a carbon and a carbon. If we explore second bonds, we have 3 hydrogens, and here we have a hydrogen, a carbon, and a bromine, so we have a clear winner over here. So this is our 2, 3, 4. Conveniently, this is drawn in the steering wheel friendly version with the 4th group angled away. So we have this action, which is
S.
So carbon 2 is S. Let's do the same thing from carbon 3. Number 1 group, bromine. Number 2 group, 3, 4. Perfect opportunity to, whoa, do it, but look weird.
So since the hydrogen's in the front and it looks like an S, does that mean it's actually an R?
Yes, because it's just like if you look at somebody doing something with their right hand, it looks like left hand to you, right? Exactly the same thing. So you can go opposite. If you want to go opposite steering wheel, you totally can. If it's sticking right out at you, and you want to do that, I do that all the time.
Okay.
Yeah, it's correct. Whatever mental shenanigans gets you to the right answer consistently is the right way.
So if you just made yourself a model and you flipped around, like physically just turn the whole molecule so H was pointing away.
I really want to pantomime me making myself into a model in front of you and turning myself around.
Okay, but like that would where you just flip it around and look at it to where it just flips the back and then you can.
Yes. Yes, you can. You can totally take a model, and I recommend people having a model and you have color code where it goes, this is my 1 group, this is my 2 group, my 3 group, my 4 group, and you can spin it around any way you like. Or you can take it apart and reassemble it. But that does take more time, and time is always of an essence on these tests. So you don't want to be... But as a double check, if there's something that's not clear and you need to visualize it, it's a good way to use a double check. So what we would have here, now that we know that this is S, or the 2 carbon and R, is you would just label this 2S, 3R, and you're done. So you just put all of the R and S designations sequentially, 2, 3, 4, 5, etc., up at the front. Put them in your little brackets, put a dash in there, and everything else is the same. So it's super straightforward once you have your designations.
Can you show your hand trick for the 3 carbon?
Yeah. So this thumb joint is center carbon to 4. So it's sticking up and out like this. Or I think straight up at me, and then 1 to 2 to 3. Or if you want to do a redraw, you can totally spin it because this is just drawn. You could redraw this with methyl up, hydrogen back, bromine out, 1, 2, 3, and do the steering wheel. That works too. Or you can go reverse steering wheel. Or you can do that silly thing the book does where you just take these and flip them to put it in the back, and then it looks like an S, but because you inverted the stereo center with an actual physical flip, now you know it's an R. All these work. I'll be disappointed if nobody in class is like doing the robot to try to figure out what their stereochemistry is. And it's one of my favorite parts of watching people take tests. That and watching all of the physical manifestations of stress. The things people do, and they're like really agitated in the middle of an exam. It's really unique, we'll say. Yeah. Well, okay. No questions? Everyone's using their hands now, and I can't tell who's asking a question. Yes.
If this structure was drawn just as like a skeletal structure, would there be a way to know if it was an S or an R, or would it be pretty ambiguous still?
Well,
having it
you can't. If you drew it like this, it wouldn't have any information about what stereoisomer you're referring to.
Okay, all right. Just want to make sure, because if you were given that, you wouldn't be able to add the S, or you'd just be able to call it and name it.
Right.
3-bromo 2-butyl.
Right, because you wouldn't have any other information about where these are oriented spatially. So this would just be a 3-bromo 2-butyl, because that's all the information you've got.
So being as specific as we can get with the given information, basically.
Yes. Yeah. And one of the cues is, if I'm really looking for that stereochemistry, I use the term unambiguously named. I did a test last time I taught this class, and I did that, and not a single person gave me the R or the S, because it was a cyclic compound, and they were like, no. And they're like, oh yeah, that's 1,2,4-trimethyl cyclohexane, and like minus something. I'm going through. I'm like, nope, and nobody. And I think I even like wrote in capitals, unambiguously. And everyone's like, duh. It's unambiguous to us. I don't know who's reading this. But everyone's just in a hurry, and they weren't looking for stereochemistry. They were so stuck in just numbering it and getting the name right in the absence of stereochemistry. They didn't recognize this as a stereoisomer.
So that would just be like one range, 1S, 1R, 1S, something like that.
Or something, 1, 2, 4 something.
Yeah, so this would be a 1 something, 2 something, 4 something. Good. Let's do it. We have the technology.
Could they all be S or R?
They see, what's so fun about this is you guys are going to learn a shortcut. Because shortcuts are the funnest. So I drew this, which implies methyl. And we'll put in the hydrogens. So 1, 2, 3. So this is going to be a 1,2,4 trimethyl cyclohexane. Let's start with 1. Which one has priority? Carbon 2, carbon 5, the methyl group. I'm not even going to insult you guys by asking about the proton. Oh, really? Does it now? Students and your counting. I lost the ability to count a long time ago, and you already know for a fact I have no idea what day of the week it is. Or what day tomorrow is.
Because it has two C's attached to.
Yeah.
Yeah.
Because this carbon has a single hydrogen and carbon, and this one has a hydrogen and a carbon.
Yeah.
So this is our highest priority group.
We actually did it. I'm so proud of you.
Huzzah.
This is a very rare occasion.
2, 3, 4. Perfect opportunity for the thumb. S. Or you could go inverted steering wheel, because you'd be turning what looks like to the right, but the steering column's pointed at you instead of away from you. What about this one? This is going to be our first priority. Same reason. Second priority. Third priority. Fourth priority. R. So here's the trick. On a cyclic system, notice that these are on the same side of the ring, down and down. But it switched S to R. So as you go around a ring, things on the same side switch. They go S, R, S, R, S, R as you go around the ring. A really common mistake people make is they'll do this one, see that it's down, see the methyl here, see it's down, and give it an S automatically. I still, if you really want to make sure you're getting all the points or actually know you're getting it right, I still prioritize anyway, but you're going to see this alternating pattern. So if you get something that disagrees with that alternating pattern, then you might want to evaluate that. Yeah.
So then for the 4 carbon, with that one, because it had the pattern, even though it's on the opposite, so because it's on the opposite side, you'd go SR, SR, but then you'd flip it to S because it's on the opposite side.
SR, SR, S. Let's find out.
It has all the same groups.
Let's find out. Yeah.
Okay.
You should. I'm sure there are going to be exceptions to this. You usually see this rule applied on cyclo rings because you're alternating top, axial, equatorial. But let's see how it pans out here. So going this way is going to be our highest priority side. So this will be our 1 side, because we're going to run into a carbon with another carbon attached to it first. This carbon has 2 hydrogens. This carbon has 3 hydrogens. So, wait, what am I doing? What am I doing?
Yeah.
Whoa.
Yeah.
Too much blue. Too many blue things. I need another color.
There's green behind you. Green.
Green. Green it is. 1, 2, 3. S.
How do you decide between the 1 and the 2?
So this is a CH2, that's a CH2, so they're equivalent. So you have to go up another one.
Okay.
And here we have a carbon with a carbon and a hydrogen. Here we have a carbon with a carbon and 2 hydrogens.
So just follow the chain.
You just keep going away 1 bond at a time until you identify a difference. And if there's no difference, that's symmetrical, and it's no longer 4 distinct groups, and it's achiral. Yeah?
Does that alternating trick work on cyclic compounds that aren't hexane? Like if you had a...
No, no, it won't. Because you have an odd number.
Yeah.
So if it worked on this,
S, R, S.
S, and this was S, and this was R, you go S, R, S, R, S, R, S. So it would work half the time.
Anytime.
It would work anytime, half the time.
So we're gonna.
So yeah. So perhaps don't lean on the that I would as a test taking strategy. Unless you are so strapped for time, you have to have an answer of some kind to make sure you don't get a 0. I would just identify the groups and assign them. That's your your best. Yes.
When you write out the whole name after you do like the parentheses 1s, 2r, 4s, do you put a dash after the parentheses?
So this will be a 1s, 2r, 4s, 1, 2, 4 trimethylcyclohexane. Yes.
So for the naming, do you have to list the numbers again to indicate the methyl group?
Yes,
Methyl groups are?
you do. Yeah, because you wouldn't always have trimethyl. So yeah, you do. Yeah, the nomenclature on the other side doesn't change. You got questions? Yeah.
What? This is just a note.
We had a tie. We'll start in the back.
Can you say the name of that compound just one more time to make sure?
If you have, is there a higher prefix than tri? So you had 4
Tetra.
methyl? Okay, so you really just keep going.
Penta, hexa, hepta,
Okay.
octa. Yep. I think somebody just said too many syllables, which is great because this our administration is trying to get us to write things in smaller doses because what's the phrase too long didn't read? TLDR.
Yeah.
Yeah, it's like that pretty much is like all of OChem right there. All right. I'm not cool. Don't worry. I don't think I am. It's never going to happen. I never was, even when I had the ability to be. Yeah.
Just to make sure I'm looking at this the right way, for carbon number 2, which is the highest priority?
Let me just do a quick clean it up a little bit.
He erased that one because it got in the way. 1, 2, and 3 ones.
Okay. So for carbon 2, we've got a carbon and a carbon and a carbon. This carbon has 3 hydrogens. This carbon has 2 hydrogens. This carbon this carbon has just 1 hydrogen. Or you could also think of it, this carbon has only 1 carbon attached, or this carbon has no carbons attached. This carbon has 2 carbons attached, or 1 carbon attached. This carbon has 2 carbons attached. So this is going to be our highest priority group. Second highest priority group, third, fourth. R.
Wait, can you just reiterate how you discriminate between 1 and 2 for priority?
Yes. So this, because we have to go 1 bond away at a time. So this bond identifies a carbon, this bond identifies a carbon, and this bond identifies a carbon. So at this point we don't have any, at 1 bond doesn't solve it. So then we move 1 more bond away. And in this case, when you move 1 bond away, you have 3 bonds. Here you've got 1, 2, 3 bonds. Here you've got 1, 2, 3 bonds. So you have to look at the spectrum of all those bonds. So what we're going to do is this carbon has functionally a hydrogen, a carbon, and a carbon at that extra bond distance. This one has 2 hydrogens and a carbon. And this one has 3 hydrogens. So when we start to look at this extra bond distance, you can see that because we have equivalency here, but here we get priority. And then the same thing applies here. That help? Yeah. Good. Other questions? Yes.
Yeah, please about the configuration of the carbon 4. Why it's because it's the hydrogens, you have to go over.
For this one? Oh, why it's S?
Yeah.
Okay, so let's take a look at that. So when we're looking at, let's erase this. So for carbon 4, it's kind of the same rationale. We've got a CH3 here, so we've got a carbon here, and a carbon here, so we need to move another bond away. This carbon has 3 hydrogens. This carbon and this carbon both have another carbon and 2 hydrogens. So we know both of these 2 positions, although they're identical, are higher priority than this position. So then from here to make up our mind, we have to move up another bond to find a difference. And when we get to this carbon has a carbon and a pair of hydrogens. And this carbon here has 1 carbon, 2 carbons, and a hydrogen. So equivalent, carbon to carbon equivalent, hydrogen to carbon, this gets priority. So this whole side gets priority. So this is our first group, second group, third group, fourth group. We can use the steering wheel, and we get S. There is one more section of this chapter, nitrogen and phosphorus acting as asymmetric centers, and it's actually kind of topical because you asked a question about ammonia being chiral. So nitrogen and phosphorus can have asymmetric centers. So if nitrogen is got 4 distinct groups attached to it, which means it's going to carry a positive charge and need a counterion. Just like, so nitrogen likes to have a lone pair, but because it's basic, it can grab a proton and be a weak acid. So like ammonia to ammonium, I'll just actually, because this is an equilibrium. But if you have 4 groups around it like this, but all 4 groups are distinct, so I've just got a methyl, ethyl, and propyl group around this. This is an asymmetric center. If you do the mirror plane and draw the mirror image, it will be non-superimposable. That will be an enantiomer. When nitrogen can't is if we deprotonated this, satisfy the charge, and we still have an ethyl, a methyl, ethyl, and propyl group. But in this case, what can happen is we can get an inversion where as a high energy intermediate, this becomes planar, this becomes planar, this becomes planar.
Yeah, just like
And instead of having an sp3 hybrid, we have an sp2 hybrid. And this is high energy. And whenever you have a high energy system, it can do one of two things. It can go back to where it came, and these three groups can get pushed down, or these three groups can get pushed up and the lone pair can end up here. And because you have the ability to invert, if we just take this, flip it back over and spin it, you'd see that it is superimposable when you do the mirror image. So lone pairs don't count as distinct groups in this particular case. But nitrogen, if you have 4 actual groups attached to it, can be an asymmetric center. And the same thing goes for phosphorus. And I'm just going to draw one fast because we're about out of time. If you have phosphorus compound, this would be a phosphorus compound which has 4 unique groups around it. And if you did the mirror image of it, you would find that it's non-superimposable, and therefore you can have a pair of enantiomers around it. So, although it's rarer than with carbon, it can happen with nitrogen and phosphorus. See everybody on Monday, review day. Bring questions. So you guys know, I'm not doing some just like comprehensive review because I can't come in and do all the lectures again. So come with questions and I will address questions on Monday. You won't need more. I would not spend any more energy on it except for general awareness. Yeah, they're not high impact.